Cool. So tonight is the Battle of Winterfell, and those of us that have been watching this show are very excited. So we wanted a Game of Thrones theme here, but we also have, the established houses on the top there, and the RISC-V free folk and the do-it-yourself crowd on the bottom. So this, what's the utility of soft processors and processor arrays? Well, for single cores, they're quite mainstream now. And they let you run your software in the FPGA, so you don't need a separate MCU or whatever. We use them to use legacy software stacks, so fat file systems, USB, networking, Linux. You can even run a full FPGA toolchain in the FPGA to generate the next bit stream of that FPGA is where we're at now. And we also use them in housekeeping stuff, booting, link calibration, and stuff like that. My interest is in using thousands of cores in overlays to build frameworks to help software developers get their parallel software running in a spatial FPGA fabric. So how can we allow a software approach that still can light up and use 1,000 block RAMs or a couple of thousand DSPs per clock cycle? The use of software-first methodology and overlays means that the turnaround time per iteration is a couple of seconds to do the recompile, not 5 or 10 hours through the OpenCL to FPGA flow. Because you have all these processors that are tightly coupled to custom function units and accelerators, that means those accelerators are 2 or 3 cycles away rather than 100 cycles away over PCI Express. And these things have been used very effectively already in Catapult, Bing Ranking, and Brainwave, and other places. So turning to RISC-V and the battle of the instruction set architectures. In the old days when we were building soft processors in 400 LUTs, we of course built our own instruction sets, and that meant we had to do our own compilers and tools and simulators. About 20 years ago, Neos and Microblaze came out, and they were so competent and had system on programmable chip builder and other tools. That meant that naturally that's how we would build soft processors. But they are they're not vendor neutral, so if you use a Microblaze software stack, you're stuck on Xilinx chips and vice versa. And there's no 64-bit extensions and so forth. You can, of course, say, I want to access the giant ecosystem of Linux, I want an x86 or ARM processor, but I want to add new instructions and stuff. That's very challenging given the licensing and architecture review board approaches of those two ecosystems. On the other hand, with RISC-V, you can run that stuff on every FPGA. It's free. They anticipate and welcome extensions. There's a vast community now. There's lots of collateral for building systems, so you can focus on what's unique in your design and let the other guys do the compilers, libraries, runtimes, test specs, and all that stuff. It's a clean, modern ISA. It's a pay-as-you-go modular approach, so if you only want to do a small 32-bit MCU, you don't have to do 64-bit floating point and all that stuff. As Mike Butts mentioned, they've left behind 20 years of legacy instruction set layers. You can just build one ISA. And I've found it sufficiently FPGA friendly to build a very small soft processor. So in the same way that compiler research now all accrues to LLVM, that's where it's done. I think we're entering an era where computer architecture research around instruction set innovation will all happen around and accrue benefit to RISC-V. So that's where, as a research community and as an industry, we ought to be coalescing. So here's what I'm doing with RISC-V. I'm building massively parallel processor arrays. So first I build a very small processing element called Groovy, the Gray Research RISC-V. It's about 300 LUTs. And in a 1,000,000 LUT FPGA, you can have thousands of these. So I put them together in clusters. In this case, the cluster has 8 processing elements going into 128 kilobyte shared memory. You can put several hundred of these clusters on a die. You can couple accelerators directly into the multi-banked shared memory as well. And you'll see there's no caches in this design because they're too expensive and cache coherence is hopeless at this scale. Now to compose these clusters together, that's done through message passing. I use a hoplite NOC. I build 300-bit wide channels amongst each cluster, so you can send or receive 32-byte messages per cycle. All the composition at scale is through message passing. That's also how you affect memory DRAM accesses. And across the whole chip, you use a partitioned global address space. So every cluster has its own address, and the memory in those clusters are unique. So in a Xilinx Virtex UltraScale 9, here's a design with 7 by 30 array of clusters. So that's 210 clusters, or 1,680 32-bit RISC-V cores, using 26 of the 30 megabytes of SRAM in the UltraRAMs on that chip. How do you program this? Currently, I use bare metal, threaded C++, and message passing. No one else will want to use that model. The plan is to deploy OpenCL on SDXL for RTL on this. So it'll be an OpenCL programming model on the host where you allocate DRAM, copy it to the device memory, and launch kernels. On the FPGA side, the groovy Phalanx couples to the SDXL shell and its DRAM channels. Now, currently, I've got 32-bit processors, and that isn't a great match for Amazon F1 16 extra large, which has 1.5 terabytes of RAM. So I really need a larger address space. So I'm currently building a 64-bit extension to Groovy, called Groovy. And it's a latency-tolerant design, so it can do out-of-order retirement. It's a very area-efficient way to absorb the memory latency going through the cluster interconnect to RAM, or going through multi-cycle function units. So this is also a compact soft processor, 400 to 500 LUTs. It's quite fast. The cluster gets better. You get 8K instruction memories. You get 64-bit channels to memory, and the whole system's designed to run faster. So it's about 3 times the bandwidth into the cluster memories. I'm also looking ahead to porting this to the Virtex UltraScale 37 and the other HBM2 devices, where the challenge is how do you move 400 gigabytes per second up and down from the processor arrays to the DRAM channels at the base of the die. I currently have a design that's about half the bandwidth I need, so I may have to double cycle the NOC. So for this community, here are some engagement opportunities and some open questions. There's a RISC-V Foundation. There's a soft processor SIG that's just starting, that's led by Guy and Tim Ansel. Some of the things we can work on there are vendor-neutral RISC-V platform profiles for low-footprint FPGA SoCs, -Zfinx, which is floating point in the integer register file, which will be great on Stratix, Agilex, and Versal. The -V vector extensions, which is how we're going to get the next factor of 4 efficiency over just instruction-based execution. And we need to have a common way of composing the cores and the accelerators and custom function units so that we can have good composition across our community. I won't go into the last topic, which I think is very interesting, about non-traditional memory models. The RISC-V ASIC people are all thinking about coherent shared memory Unix systems. We're thinking about how do you access 1,000 memory accesses per clock cycle. It's a different kind of problem, and we have some interesting work there. So finally, the prediction here is that all of the non-RISC-V soft processors will eventually fall to the army of the dead, and everyone will be running RISC-V soft processors on all these FPGAs. Thank you.